Okay, hi everyone. So for this video, I will discuss the empirical rules in describing datasets. So basically, for the first one, usually an observed phenomenon in datasets is that it follows this bell-shaped curve. So this bell-shaped curve is called the normal distribution. So one important property of normal distribution is that the mean, the median, and the mode coincides with each other, which is shown as this pink, no? Ito, pink or red bar here. So one rule no is that when it is within one standard deviation, uh, within the mean, then all of the data is or the data set has 68% or the values are within the within this one standard deviation, or sorry, so this the 68% of all values fall within this one standard deviation. And if we extend this, no, instead of just one standard deviation, if let's say we have two standard deviations, so from here to here, then it will be containing, okay, then it will be containing 95% of the values. And then if you go on about here and somewhere here, so if this is we have three standard deviation, then it will be, I think this will be too much, no, ganito lang pala, no? Yan. So this will contain 99.7% percent of the data sets. Okay, so let's say we have an example here. We have the sample daily salary of employees who work in restaurants in a large city has a mean of 600 pesos and a standard deviation of 75. So using the empirical rule, so 68% of the employees there will have, no? So the solution for that is it will lie in between 525 and 675. So again, 68% of the employees will have a range of 525 pesos to 675 pesos. Okay, for the employees with 95%, or the 95% of the employees will lie on two standard deviations of the mean. So 95% of the employees will have 450 pesos to 750 pesos as their salary. Okay. So another empirical rule that we should discuss is the Chebyshev's theorem. No, actually, this is not an empirical rule per se, but it is empirical in a sense. No. So the Chebyshev's theorem basically means that if your data set has a standard deviation of k, then at least 1 minus 1 over k squared will be the number of values within that data set. So for example, let's say if you want to figure out how many of the data is within this standard deviation of 1, so Chebyshev's theorem will always say that at least 0% will be within this standard deviation. And then if no, we have these two standard deviations k, then it is possible that at least 75% will be within this region, and so on. So we have 3, so 88.9, 4, 95%, oh sorry, 4.472, 95%, and 10, that will be 99%. Okay, so that will be all for the empirical rule. So to finish this off, no, I will also discuss the measures of relative possession. So for the measure of relative possession, we can gauge, let's say, what is the data at the 99% portion of the data set, or at the middle of the data set, or at the 25% of the data set. So instead of just calculating the central tendency, the middle, we can also find the quarter, no, or the quartile, or the deciles. So we have the z-score to help us find the relative position of the data. So for the sample, we have z is equal to x minus x bar over s. For the population, we have the z-score is equal to x minus mu over sigma. So we have the same formula, guys. No? So this is the mean for the sample, the mean for the population, the standard deviation for the sample, the standard deviation for the population. So this z-score is a way to represent the position in the bell curve or the normal distribution. So what does the z-score mean? So the ordinary values of the z-score lies within the two standard deviation, no? And if it is beyond this two standard deviation, it is an unusual value. So as you can see here in this graph or this diagram, that the if the z-score is negative, then it will be less than the mean. And if the z-score is positive, it will be greater than the mean. So the zero, guys, is actually when z is equal to zero, then the data lies within the mean. No? So again, no, again, the z-score represents this position in the normal distribution. Okay? So we will discuss it later on the normal distribution topic. Okay? So usually we normalize so from the population scores, we can standardize pala, no? We can standardize this distribution into its normal or in its standardized score, which is the z-score. Alright, sige, later na lang yan ma-discuss. Okay? Ayan. No? So let's say we have an example here. Suppose we have SAT scores among college students which are normally distributed with a mean of 500 and a standard deviation of 100. If a student obtain a score of 700, what should be his z-score? So the z-score will be x minus so what do you call this? Population mean over sigma. So this is a population, guys. Now since SAT scores, okay, are a census, no? So we can gather everyone's SAT scores. So the population mean is 500 and the standard deviation is 100. So therefore the z-score is 700 minus 500 over 100, which is equal to 200 over 100, which is equal to 2. So if the z-score is positive, then therefore, okay, the score of the student is above, no? The score of the student is above the mean. So basically, as you can see here, the mean is 500, the student score is 700. So if you can draw this, so if this is the mean, if this is 500, so this is the average, the score 700 will be positive, no? Which is greater than 500. And also, we can say that this is how many standard deviation, no? So we have two standard deviations from the mean. So basically, this is kumbaga yung percentile niya is 95%, right? 99.7 nga ba? Forgot this. I always forget this. Let's see. Ayan, no? So we have 95% lang pala, no? 95%. So 95%, so that is his ranking in some way, a ranking, no? For his score. Okay? So another example here. So a group of data with normal distribution has a mean of 45. If one element of the data is 35, will the z-score be positive or negative? Yeah. So it has a mean of 45 and the data is 35. So is the z-score positive or negative? So the z-score must be negative since the element is below the mean. And also if you calculate its z-score, even not knowing the sample standard deviation, we can calculate that it is negative. Okay, so moving on, we can also find or determine the quartiles of our data. And this is not limited to quartiles only. No, we will discuss deciles and percentiles. But basically, for quartiles, we can find we can divide the data into 4 chunks. And the quartiles is just finding the first quarter of the data, the second quarter of the data, and the third quarter of the data. So the formula for finding Q sub K is equal to this. Okay, so we will utilize this later on, no? So we will have more context later with regards to how to use this formula. So the visualization of the quartiles is a ranked score divided into 4 equal parts. And also, let's say you have all of the data in this number line. So if you divide this data by 4, you can find the quarter 1. So this position here, the data position here is the quarter 1. So the data position here is the quarter 2. The data position here is the quarter 3. So the quarter 2 is actually also the median. So with regards to the order of the data, the quarter 2 is also the median. Ano? So this one is the minimum of the data, maximum of the data. And that's so how do we find the quartile of the data? We have, let's say we want to find quarter 1, the median, or quarter 2, or quarter 3. So we have an example later. Okay, so just a brief overview of this. So for Q1, Q2, and Q3, so the first quartile or Q1 is the separation between the 25 to what? Separates from the bottom 25% to the 50%. 75% pala, no? And then the second quartile separates the bottom 50% of the sorted values to the 50%. The third quartile separates the 75% and the 25%. So basically, ang ibig sabihin lang nito, we have here 25% and then we have 75%, no? So for this one, we have 50-50 separation. And then for this one, we have 75 and we have 25. Okay. So again, quartiles is just one of the ways to measure relative position. We can also calculate the percentile. So the percentile, instead of quarters or 4 divided by 4, we have percentiles, which is dividing by percent, 100. And deciles for dividing this by 10 slices, no? So an example here. So find or the following are the number of defective items produced in a month for the last 24 months for a certain manufacturing company. So calculate the 95 percentile and the first quartile. Interpret the results. Okay, so we have this data set, and the first thing we should do if we want to find the measure of relative position, which is the 95 percentile and the first quartile, is to arrange this first as in ascending order. Actually, you can also arrange this in descending order, but it should be always in ascending order. So arranging this into its ascending order, okay, I already arranged this for brevity. So how do we now measure we're trying to find the 50, the 95 percentile, and the first quartile. So to calculate the percentile, we have P95. We have the formula, no? If you can recall, we have this to calculate the percentile. So the key here is 95. So we can just substitute the 95 there. So we have 95. And then we have n plus 1. So what is n here? So the n here is the number of data sets. So it is already given. We have 24 months, which means we have 25 data sets here. So this will be 24 plus 1, and then all over 100. Okay? So the P of 95, that is equal to, sige, let's calculate this. 95, 25, Okay, I already added this, no? So this will be 23.75. So 23.75. So meaning it is in the 23.75 place or observation. So we have to count 23, no? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. Okay, so as you can see, this is the 23 observation. Therefore, your 23.75 lies in between these two. So how do we find the 23.70 no? Position here? So for that, we want to utilize this decimal place, no? To calculate for this in between here. So we have 0.75 times, so this is in between 40 and 45. We have 40, we have to, actually this should be 45 minus 40. Okay, so we just have to add this to our 23, sorry, at our 23 place, which is 40. So this will be equal to 40 plus this. So 40 plus, we have 0.75 times 45 minus 5. So we have, sorry, 40 minus 40, 40 pala ito, no? Ayan. So this will be 43.75. So this is your P95, no? So the data set at P95%. Okay. So for quartile 1, so Q1, this will be equal to, so we're trying to find for K is equal to 1. So we have 1 plus N plus 1. So we have 24 plus 1. And then K here will be, sorry, N will be, sorry, the denominator will be 4. Ayan. So we have 25 over 4. So calculate 25 over 4. Okay. So this will be 6.25. So this is the 6.25 place, no? In the observation we have here, 1, 2, 3, 4, 5, 6. So somewhere in between this is 6.25. So therefore, this will be 6 plus, so this is in between 18 and 20. So we have 20 minus 18. And then multiply this 0.25. So we have, let's calculate this again. I think this is 2. So the answer is 6.5. Okay. So that will be all for this problem. All right. Okay. So, moving on, we can actually utilize this data, this quartile 1, quartile 2, quartile 3, the minimum and the maximum, to display or to describe the data set in form of a diagram. You know? So we have a box plot to represent the variable, what do you call this? The summary of the data with regards to how low or what is the minimum value, what is the maximum value of the data, the median, and the quartile 1 and quartile 3 of the data. So as you can see here in this plot, we can see that the minimum is has this stick, no? And then the maximum has this other stick. And then we have the box that represents the range of the quartile 1 and quartile 3. And the middle portion of this box has the median or also the quartile 2. Okay. So we can actually also describe here the skewness of the data. Okay, more to that later, ano? So if it obeys a normal distribution, then it will have a balanced graph, no? Just like this. But if it is a skewed distribution, so there is an imbalance in the data, then it will look something like this. No? So more into skewness later. No? So the skewness can actually be calculated using the mode or the mean. So using the mode, we have x bar. So the mean, no, mean minus the mode over the standard deviation, or we can use the median. We have 3 times x bar minus the median, no? X tilde over S. So the measure of skewness, how do we describe this graph? No? So we have this, if it is balanced, no, or symmetric, then the mode and the median and the mean lies in the middle, no, which is a normal distribution for. And if the distribution, the mean is into the left, then it is skewed to the left. So if the mean is less than the median, okay, and the mode, then it is skewed to the left. If the mean is greater than the median and the mode, then it is skewed to the right. That's it, no? Yun lang naman yan. And then for outliers, so for outliers, how do we describe uh, the data set with outliers? No? And what are outliers in general? No? So an outlier is a value that lies very far away from the vast majority of the other values in the data set. So again, what I'm trying to say before is that let's say you have a data set. So let's say you graph the data set. The data set is, let's say this third data set, no? This lines here. An outlier is when one of the data or more than one of the data is outside of the vast majority of your data set. So this one is called an outlier. Okay, so it will help us usually to remove the outliers, to remove the or to lessen the variation of the data, you know, because it has a dramatic effect on the mean and the standard deviation. And an outlier can usually reverse the nature of describing the data in its brief form. So kumbaga parang uh, instead of calculating with outlier, we can just remove the outlier to see the vast majority of the data's behavior instead of incorporating the outlier. Oh, okay, so box plots are a way to describe uh, the 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 what do you call this? Nalimutan ko na tuloy, no? The skewness na lang, no? The skewness of the data. And we can modify this by also providing an outlier, no? Or checking if it has an outlier. So the modified box plot, we can uh, we can also pinpoint where is the outlier, and this is the majority of the data. So how do we know if a data is an outlier? No, that is one of the questions. So it depends, no? So there are ways to remove the outlier, but that will be part of the person. No? Okay. So basically, the rough approximation is that it will be uh so far, no, from the majority of the data set, which is this. Okay, so that's it. And thank you guys.